Good morning, everyone. So last time we discussed so we've already seen one algorithm, right? For minimum cost perfect matching in bipartite graphs, the Primal-Dual Algorithm. And it's very simple in the way it works, right? It's a very short pseudocode and conceptually it's very simple. Of course, it comes at a cost, that simplicity, which is that it's not clear if that algorithm terminates in polynomial number of steps in just the number of the vertices, right? In fact, the analysis we did shows that it does not. Right? There might be a better analysis. I don't know the answer to that yet. It's not going to matter because we are going to see an algorithm which has a simple analysis that shows that it is actually polynomial time in the number of vertices. Okay, so that's the algorithm I want to discuss today. And in particular, I want to remind you of a certain subroutine, which I'm not going to write down. So let me see. Let me share the other screen. Okay, so I want you to recall the algorithm we covered for just finding a perfect matching in bipartite graphs, right? And we are going to use a certain part of that code as a subroutine in our current discussion. Okay, so right, so we start with any maximal matching, or you can start with the empty set if you like, and you start with some augmenting tree, and then you have the following loop. And so what it does is it takes a matching, so just the code within this loop, it takes a matching and it takes an it takes an m alternating tree with respect to that matching m, right? And it does one of three things. The first thing is that it finds an exposed vertex and gives you a bigger matching. So that's what we are going to call outcome A. You get a bigger matching at the end of this subroutine. Okay. Um, Otherwise, if it doesn't find an exposed vertex, it might find a vertex which is already covered, in which case it will include that vertex and its neighbor in the alternating tree. So the alternating tree becomes bigger. That is what we are going to call outcome B. Okay. And finally, if neither of those happen, right, so you've reached a situation where all the black vertices of the tree, I mean the U vertices of the tree, they do not have any white neighbor outside the tree, right? At that point, you have reached a situation where you have a deficient set, and that is what we are going to call outcome C. Okay, so just remember this subroutine. I'm going to write down the three outcomes, and we are going to use this subroutine inside our algorithm that we are going to discuss today, right? And as usual, I won't write down the actual algorithm first. We'll just go through an example, and then we will formalize it. Okay. Oh, I see. Oh no, this is not right. I need to change the screen I'm sharing. 1 second. All right. Okay. So let's start our new page. So the main question we are answering in the affirmative is there an algorithm for min cost perfect matching for bipartite graphs that runs in time that is polynomial in n? Okay. And just to keep a track of the subroutine, so the only thing I'm going to write down is the following. So we have got a subroutine, and it has three outcomes. So outcome A is going to be, right, so the input is the tight graph H. That is what we'll be giving it as an input. We'll give it a matching M, and we will give it an alternating tree T. Okay, so this is generally going to be, in our context, it will be the tight graph. It's any matching in the tight graph, and this will be an M alternating tree. Okay, M alternating tree in H itself, not in the big graph G. And the three outcomes are going to be either it returns, maybe let me just say, increases the size of the matching. The second outcome is going to be that it increases the size of the alternating tree. The number of vertices in the tree. And the last outcome is going to be that it finds a deficient set. S subset of U in the graph H. All right. All right. So let's start with our same example as before, except that now we are going to use a slightly different algorithm, which will then analyze and conclude that it is actually polynomial in the number of vertices. Okay. Are there any questions or concerns at this point? Okay. So here is the graph. U0, U1, U2. W0, W1, and W2. And we have all possible bipartite edges except for U1, W0. And the costs of the edges are 4, -2, -2, -2, 2, and let me just, and finally we have 1, -2, and 0. Okay. Okay, so that's our given graph G with the edge cost C. And we want to run the algorithm that we are going to formalize on this, right? So let's start step by step. So of course, in the beginning, I'm just going to choose the empty matching, and the alternating tree is going to be any exposed vertex with respect to that matching in the U set, right? So as usual, we have G is U, W, and the vertices V and edges E. So V is, of course, U union W. Okay, so initially we set the matching to empty, and let's say the tree is U0, comma the empty set. That's your set of edges. And of course, we want a dual feasible solution at each step. So we'll also fix a dual feasible solution. In fact, in some sense, yeah, in some sense, you want to first fix the dual feasible solution and then look at the H graph. But of course, the empty matching is going to be a matching even for the H graph, right? So it doesn't matter. So the dual feasible solution is going to be usual. You're going to take the minimum cost over the edges and divide it by 2. Right? So let's start with usual DFS. Okay. And let's draw the H graph at this point. So we will have all the edges whose cost is exactly -2, right? And those are, I think there are 4 edges, 1, 2, 3 and 4. Yeah, the screen is not working. Sure, I'll write a bit larger. Yeah, okay. Okay, so far everything is visible. Okay, I'll make the handwriting a bit bigger now. Okay. All right, so that's our H graph. And so let's now call the subroutine. Okay. So let's call, I'm just going to call it subroutine because we only have one subroutine with the parameters H, M, and T. Okay. So at this point, we have the alternating tree that we have is simply one vertex U0. And we look at its neighbors in H. And of course, immediately we run into an exposed vertex W1. So I might as well just consider that, right? So the W1 is an exposed vertex. So I'm going to take the symmetric difference of my current matching with this edge, and that's just going to give me a matching bigger by one edge. Okay, so that's very straightforward. I just want to write down each step. So this is we are at outcome A. We get a bigger matching, right? And the bigger matching is simply U0 W1. Okay? Because our augmenting path is a sort of a trivial path, it's single edge. All right. And notice that at this point, what we have is not a perfect matching of the tight graph H. Of course, if we find a perfect matching of the tight graph H, we are done. We have a min cost perfect matching in the original graph. Okay. All right. Let's repeat. So what has changed now? Okay. So now we need to initialize the tree again, right? So we're going to pick another exposed vertex and we are going to make that the root of the tree. So I might as well pick U1. So let's say my new tree is the exposed vertex U1 and the empty set of edges. Okay. And now let's call the subroutine again. H, M, and T. Okay, so what happens this time? This time we are starting at U1 and we look at U1's neighbors in the graph H. And there's exactly one, that's W1, which is not exposed, right? So we add W1 to our tree and we also add its neighbor. Right, so keep track of the matching. I'm not going to draw the matching right now. Okay, so the matching right now is U0 W1. So I also have to take its neighbor U0 and this is a matching edge. So maybe I'll just keep track of the matching in the trees I draw. Okay, maybe let me make the font a bit bigger. So this is U0 and this is a matching edge. Okay, and now we are at U0 and we have two neighbors W1 and W2. W1 is already taken and now we take W2. Any questions? All good? Okay. So let's take W2. This is exposed vertex. And so we basically have an M augmenting path here. Okay. And let's take the symmetric difference of our matching with this path. So that's quite straightforward in this example. We get U1 W1 and U0 W2. And notice that once again we are in outcome A of the subroutine. Okay. And once again, the new matching is not a perfect matching of H. And we continue the algorithm, but we need to reset our tree, right? So at this point, our matching is two edges, U1 W1 and U0 W2. Okay. So the only exposed vertex on that side of the graph is u2. So our new tree is going to be u2 and the empty set of edges. Okay. Okay, let's repeat. Let's call the subroutine again. Okay, so this time what do we get? We already have a matching of size 2, right? And you can already observe in this graph H that the maximum matching has size 2. So you know what the outcome you're expecting is. So let's just do it. So let's start at U2. And what are the neighbors of U2? Well, there's only one neighbor, W1. And W1 is already matched with U1. Oh, okay. Right. And okay. And U1's neighbors are, that's it, right? U1 just has neighbor W1. So we stop here, right? And at this point, we are not able to grow the tree further. So nor do we find an augmenting path, right? So what we have here is a deficient set. And the deficient set is simply the U vertices in this tree, and the neighborhood will be simply the W vertices of this tree. So we have the deficient set U1, U2. So this is a situation where we have run into outcome C. We have found a deficient set. Okay, so this is our deficient set, and the neighborhood of this set in the graph H is simply the vertex W1. Okay, so well, if we find a deficient set, what we did in our original algorithm is we updated the dual feasible solution, right? And the deficient set basically guides us in how to update the dual feasible solution. So that's exactly what we're going to do. Let me mark the deficient set and the neighborhood here in this graph H. So U1, U2 is our set S found in this iteration, and the neighborhood is W1. Okay. And now we are going to look at a set of edges. I'm going to change the notation slightly, but it's the same meaning. So we are going to look at the edges which are going between the set S. So they have one end in S, and the other end, I'm just going to write it simpler, right? It's basically W, the color class W, minus the neighbors of S in the graph H. I think this is actually a much better notation than what I used last time. Okay. So let's look at this set, and let me make some space. Okay. Okay, so let's look at this set. What do we have? The edges going from U1, U2 into all the vertices except W1. So what is that? We've got U1, W2, and we have got U2, W0 and U2, W2. Let us compute their slacks. Well, I happen to remember, and I think I've written in the same order, so there should be 4, 3, and 2. Can you please check? Is it correct? 4, 3, and 2? Okay, cool. So this minimum slack is this guy. And so we are going to add 2 to all the vertices in S and subtract 2 from all the vertices in the neighborhood of S. And that's going to give us a new dual feasible solution. Okay. So what do I want to do? Do I want to make the changes here, or okay, let me just make the changes here because I really don't want to go to another page as far as possible. Okay. All right. So we are going to add 2 to U1 and U2. So this minus 1 is going to become a plus 1. This minus 1 becomes a plus 1. And for W1, we are going to subtract 2. So we get a minus 3 over here. Okay, all the others remain as they are, so I won't write them, overwrite. Okay, so what we have done in this situation, in outcome C, we have updated the dual feasible solution. Okay, notice, however, okay, maybe we should draw the new graph and then we can notice that. So let's draw the new tight graph and see what happens to our M and T with respect to the new tight graph. Okay, so the new graph, I just need the vertices and edges, so I think I can draw it here. U0, U1, U2, W0, W1, W2. Notice that the edges between S and the neighborhood of S and H, all you have done is you have added plus beta and you have subtracted beta, right? So those will remain tight. So let me just draw them. Right, so these will remain tight. And the edge which has no end in either of the two sets, the dual variables have not changed, so that will also remain tight. So U0, W2 should remain tight. The only tricky one is the edge going from the neighborhood of S in H to outside the set S. Right, so the only edge that may stop becoming tight in this example is U0, W1. And in fact, it stops becoming tight. You have subtracted epsilon or beta on one side, and you have not added anything on the other side. Right? And an edge becomes tight, one that was not tight earlier, which is U2, W2, using which we chose our slack, right? The beta value. So this becomes tight. So these are our 4 new tight edges. And let us look at our matching from the last iteration, right? We haven't changed the matching since this call of the subroutine, right? So the matching we have here is U1, W1 and U0, W2. And that is still a matching of the new tight graph H. Okay. And the alternating tree we have is simply the vertex U2. And that is still an M alternating tree in the new graph H. Okay. So all these things are not coincidences. They happen for a reason. Right. So our M and T are still valid for the new graph, and right. So we can proceed with the same M and T. Any questions or concerns at this point? Everybody with me? Yeah. All right. So all we have done in this particular call of the subroutine is we have changed the dual feasible solution, which in turn changes the graph H. M and T are still the same. So let's call the subroutine again with the same H, M and T. So at this point, the only M exposed vertex, in fact, the tree is already there, so I don't need to. Okay, so the tree we have is U2. And now let's explore the neighborhood of U2 in the tight graph H. So we have W1 and W2, and W1 is already matched. W2 is also already matched. So let's draw both of them. We have W1, W2, and they are matched to U1 and U0. And U0 and U1 have only 2 neighbors which are already in our tree. Okay, so we can't grow the tree any further at this point. Right. So once again we have run into outcome C. Right. Okay. So once again we have outcome C here, and the deficient set in this particular iteration is U0, U1, U2. and the neighborhood of that is W1 and W2. Okay, so let's mark these. So we have U0, U1, U2 and W1, W2. And let's look at our set of edges that we care about. So they are going from S to W minus the neighbors of S in the graph H. And those are precisely two edges which are going into the vertex W0, U0, W0 and U2, W0. And their slacks are 6 and 1. Is that right? So our beta is 1. We are going to add that to U0, U1, U2's variables and subtract from W1 and W2. All good? So let's do that. And let me use a new color, maybe green. Okay, so let me add 1 to all the vertices on the left side. So this 1 minus 1 becomes a 0. This plus 1 becomes a plus 2. And this plus 1 becomes a plus 2. And let me subtract 1 from W1 and W2. So this minus 3 becomes minus 4. And this minus 1 becomes minus 2. Okay. So that is our new dual feasible solution. The vertex W0 still has the same label as the original, which is minus 1. But everything else has changed since then. Okay. And now that we have a new dual feasible solution, let's draw our graph H again with respect to this dual feasible solution. So all right, so the new H, it's going to be here, U0, U1, U2, W0, W1, W2. And what are the edges we have? Well, let's just observe all the edges in our previous H graph. They go between the set S and the neighborhood, so they will all remain tight in this particular instance. So let's just draw all of them, 1, 2, 3, and 4 edges. And finally, at least one edge should become tight, and that in this case is U2W0. So that becomes tight. Okay, so we have a new graph H. Our matching has not changed for a while now. Let's look at our matching. U1, W1, U0, W2. Right? That is still a matching in this graph. And the tree that we had, right? So the tree, actually, I think I made a mistake earlier. Yeah, okay. I did make a small mistake, I think, but in the grand scheme of things, it didn't change anything. I think in the previous iteration, I said that the tree we started with was U2 empty, but the tree had actually changed. So my bad. The tree had actually changed here. And that is what we use to get our deficient set. So, okay. So is everybody clear about the mistake? Right. So the tree we started with in the earlier iteration, the one before this, was U2, W1, U1. And remember, we are just looking at the neighbors of all the black vertices, black being the U vertices. So we would have discovered W2 and we would have added W2 and U0. Okay, so the tree actually changed in that particular subroutine iteration. Right? I forgot about that. Luckily, we got the same tree. We had to, actually. Okay, so again, in this case, now I have a chance to correct myself in a nicer way. So the tree has actually changed. So we are going to start with this tree now. And we are going to call the subroutine with the new graph H. The matching is the same. and the tree has changed, right? So this is the new T. All right. So call subroutine with H, M, and T. And let's see what happens this time. So the tree is already there. It's U2, W1, W2, U1, and U0. Okay, that's our tree. And now we are going to look at all the neighbors of U1, U0, U2 that are outside this tree. Okay. So what do we get? For U2, we get a new neighbor. That is W0. So we're going to add that to our tree. I mean, in fact, we are not really adding it to the tree. It's exposed. So we just get our path without adding it explicitly. Right? So what I'm augmenting path is simply a single edge U2W0. Right? And if I take the symmetric difference of my current matching with this edge, I get a matching bigger by one size, which simply includes this edge. Right? So we have the original matching from the previous iteration, which hasn't changed in a while, U1 W1 U0 W2, and we have one more edge U2 W0. And at this point, we've got a perfect matching in H. Okay, so again, I want to write down the outcome. So the outcome here is we got a bigger matching, and this is a perfect matching. So our algorithm is going to return M. Okay, and this is definitely a minimum cost perfect matching in the original graph with the given edge costs, because we have a perfect matching in the tight graph with respect to the current dual feasible solution. So it follows from complementary slackness interpretation. Great. Okay. So notice that we call the subroutine 1, 2, 3, 4, and 5 times. And we got outcome A in 3 of those calls and outcome C in 2 of them. What about outcome B? This example doesn't have that. It's actually very boring. You just increase the size of the tree. So outcome B, you actually don't do anything. You just increase the size of the tree and you call the subroutine, right? So in this particular example, we don't have any outcome B cases, but it's actually the least important of the 3 outcomes. Okay. So now I want to formalize this. Are there any questions or concerns at this point? Yes. Ah, right. Okay. Okay. Yeah. Good point. Right. That's right. Right. So what I mean by outcome C is that, okay, so the outcome C returns a deficient set. Whether the size of the tree increases or not is not that crucial to us. Right? So let me try to think about this again. So I see. Okay, okay, okay. I see what you mean. Right. Right. Okay. I increase the size of the tree, and then I should have ideally called the subroutine again with the new tree, and that would have given me a deficient set. Right. Okay. True. True. I think I combined a couple of things together. So yeah, technically you are correct. What would happen when you call the subroutine here is that the tree, which was just U2 and the empty set of edges, would now increase to these 3 vertices and 2 edges. And then you would call the subroutine again, and you would not be able to grow the tree anymore, nor the matching, and you would find your deficient set. So yeah, technically speaking, we did have outcome B here, and I just skipped it. Again, after that point, yes. Yeah, you're right. Yeah. Yeah, so I actually skipped outcome B. It's not that we did not have it, I just conveniently skipped it. Yeah, cool. That's correct. Okay, anyways, once I run the formal version, you can go back to this example and put down the steps that I skipped actually. But yeah, you're right. I actually skipped them. Yeah, because I was just too, I guess I was in a zone. Yeah. All right. Any other questions or concerns? So I want to write down the formal version of the algorithm, the pseudocode. Okay. So, all right. So let's go there. Let us formalize the algorithm. All right. So, well, at any point we have dual feasible. Maybe just let's just write down. So at each step of the algorithm, we have three things. One, of course, is our dual feasible solution, y bar. And then, well, once you have y bar, you get the tight graph H, right? So that's just a derivative of the dual feasible solution in some sense. And we have a matching M in the tight graph. And we will always have a valid M alternating tree, T, with respect to, well, in the graph H. Just say in H. Okay. And when we have these three things, so let's just write down what is it that we are really doing. So here is our sort of main loop. So we compute the tight graph given the dual feasible solution. And we call the subroutine, which I'm calling just subroutine, with H, M, and T. Okay. And we've got three outcomes. So if outcome A occurs, so we have a bigger matching, right? That's outcome A. The subroutine tells us that, hey, here is a bigger matching by finding an augmenting path. So of course, if this matching is a perfect matching, then you just go home. If M is a perfect matching of H, return the matching and the certificate, and that's it. Okay. Otherwise, if it is not a perfect matching, then you just continue. There is nothing to be done, right? And the other interesting point is when outcome A does not occur and instead outcome C occurs. That's when we have to do something non-trivial again. So outcome C is when we have found a deficient set. So in this case, our set S, so the deficient set S is simply going to be the black vertices of the tree, right? In fact, that is what the subroutine will already return to you, but I'm just writing it here to make it explicit. So this is a deficient set in H. And notice that, observe that the neighborhood of this deficient set in H will exactly be the white vertices in your tree. Okay. And we are going to compute the beta, which is going to be the minimum of the slack of all edges for, maybe I should write UW, where UW is an edge of the graph G and U is in S and W is a white vertex that is not in the neighborhood of S in the graph H, right? So for all of these, we are computing the slack and we are taking the minimum. And for each vertex in S, we are going to do a dual update, which is y bar U is going to be set to the original y bar U plus beta. And for each W in the neighborhood of S in the graph H, y bar W is going to be the original y bar W minus beta. Okay. And if outcome B occurs, then we are just continuing. So it was very easy to forget that outcome B had actually occurred, right? We are just repeating the algorithm and keeping on growing the tree or whatever. So the only interesting things we are doing is in outcome A and outcome C. That's when we actually need to do something, right? And let's do the initialization. Well, it's standard, right? So we set the dual feasible solution for each vertex of the graph, set the dual variable to be equal to half of the minimum of the cost of all edges. And we are going to set the initial matching to just the empty set, and the tree to be any m exposed vertex in the set U. Well, it's any vertex because it's the empty matching. Okay. Of course, I can make it more complicated and start with a maximal matching in the graph H, but then it just makes the code more complicated. It doesn't really. So I'm just going to start with the empty matching in this case. All right. So that is our formal version of the algorithm. So I just want to take a few minutes to understand this observation that when you do a dual update, your M and T are still valid matchings and alternating trees with respect to the new H, right? We observed that in the previous example, right? I just want to try to go a bit deeper into it and convince ourselves that that is happening for a reason. It's not just coincidence in this example. So let's try to understand what a deficient set looks like. We've probably seen some of these drawings before. So notice that in our case especially, the deficient set is found by looking at the black vertices of the tree, right? And the neighborhood is going to be exactly the white vertices of the tree, right? And you can actually see that the number of black vertices is exactly one more than the number of white vertices, because all the vertices in the tree are matched except for the root, which is an exposed black colored vertex, right? So what we get in our algorithm actually is a situation like this. We have a bunch of black vertices, and that is our trees black vertices, right? And the neighborhood is one less number of white vertices. and this is the tree's white vertices. And well, we are assuming our graph is bipartite with a perfect matching, right? Because we can just run the perfect matching algorithm. So what happens in the complement is we get something like 5 vertices here in this example that I'm drawing, and 4 vertices on the other side. So this is the graph H. And what are all the edges like? Can someone tell me which particular types of edges do not exist in this drawing? So I've drawn a bunch of boxes. So in the graph H, you can't have edges from one of these boxes to one of the other boxes. What are those two? Okay, top left to bottom right. Exactly. So the only edges you can have are these, right? That is by definition of S and N of S. So these are all the kinds of edges you will have in your graph H. However, in the graph G, will you have edges from top left to bottom right, or you may not have such an edge? Okay, we should have at least one. Why? Right, right. So we are getting beta from there, but the probably the more root reason is that we are assuming that the graph has a perfect matching. The graph G has a perfect matching. So if there was no edge from top left to bottom right in G, then S would also be a deficient set in G, right? So we are going to definitely have edges going from top left to bottom right in the graph G. So let me just put that with a red color, right? So we will have these kinds of edges in the graph G. Must exist in G. At least one such edge must exist in G, right? And these are exactly the edges we are using to compute beta. So of course we want a non-empty set to be able to compute beta. All right. And right. And what else? Right. So where are our matching edges? So we have a M at each step of the algorithm, right? So let's say I'm looking at the H graph at a particular step of the algorithm, and this is what my H looks like, right? This is an abstract drawing of H, right? So where are the M edges? They are on the S to NS side, but do all M edges have to be on that side? Right, so there could be some M matching edges going from the top left to the bottom left. Could there be other M edges? Top right to bottom right. You could also have those kinds of edges in general. Whether they happen in this particular example, I don't know, because it's a very small example. Right? But in general, you could also have those kinds of edges. So all the matching edges actually look like this. They are either top left to bottom left or top right to bottom right, because the entire tree's vertices are on the left side, and those vertices, except for the root of the tree, are all matched within each other, right? So all of the right, in particular, all of these three edge vertices in this example will have to be matched with some three vertices here, and this would be your root of the tree, for example, right? On the other hand, you could also have matching edges on the other side, the top right to the bottom right, right? So this green color is my matching edges. And let's think about how the graph H will change when we update the dual feasible solution, right? So edges which are going between S and N of S, they will remain tight because we are adding beta and subtracting beta, right? The edges that are on the right hand side, top right to bottom right, they will remain tight, right? Because we are not adding beta, we are not subtracting beta. Right? So the only edges that could stop becoming tight, stop being tight when going from one step to the other, are these kinds of edges, right? Because in these you are subtracting beta. So these are the edges going from the bottom left to the top right, right? So here you are subtracting beta on one side, but you are not adding anything on the other side, right? So that's an observation I want to make. So the only edges that stop being tight, okay, it's already 12:50, sorry, I'm going to conclude soon, are those from bottom left to top right. Right? And at this point, you can see why the M will still continue to remain a matching. And if M remains a matching, right, your tree edges are also there. Notice that all the edges which are on in the tree, they are still going to continue remaining in the H graph. So the tree will also remain an M alternating tree in the next step. So it is not a coincidence that although we updated the dual feasible solution and we changed the graph H, the M and T are still valid. Right? So that's the key observation. Note that M and T remain valid even after dual update. So that is outcome C. Okay, so that's all for today. I'm already beyond 12:50. So let us, maybe I'll give it as a try it yourself problem. See if you can analyze this algorithm and prove that it is polynomial in the number of vertices. Okay, so all right. So we'll continue from here on Wednesday, and I will tell you a little bit about history of these matching algorithms, and we will switch to non-bipartite matchings on Wednesday itself if possible, otherwise on Thursday. Okay, that's all for today. Are there any questions or concerns? Anybody in the call? Any questions or concerns? Okay, if not, I'll stop recording.